sugar, sulfuric acid, Dixie cups, beakers, a fume hood because gas will be produced, popsicle sticks. You'll pour the sulfuric acid into a beaker. Pour the sugar into the beaker as well with the 2-to-1 ratio. Now put the sugar in the Dixie cup. Put some water into the sugar and mix that. Make sure it's kind of moist.
As the sulfuric acid and sugar react, the reaction, or the beaker, will start to feel hot. What that means is that the reaction is exothermic. Exothermic means that the system loses heat, it exited, and endothermic means that the system absorbed heat, and N means endo. The resulting loss and absorption of heat occurs because of chemical and physical changes around us. This can be explained by enthalpy. Enthalpy, or H, is a thermodynamic quantity that relates to heat flow and can be used to explain exothermic and endothermic reactions. One way to tell if a reaction is exothermic or endothermic is by feeling the reaction. If it is hot, that means that it's exothermic. If it's cold, that means it's endothermic. But another way to find out if a reaction is exothermic or endothermic is to calculate its enthalpy of reaction, or delta H. Exothermic reactions have a negative enthalpy of reaction, and endothermic reactions have a positive enthalpy of reaction. The delta H of a reaction can be calculated in 3 different ways. 1, by finding the enthalpy of formation for the products and reactants and subtracting it. 2, finding the energy of the bonds broken and subtracting the energy of the bonds formed. 3 is by using Hess's law. Method number 1 is to find the delta H. Every molecule has an enthalpy of formation, or HF. The enthalpy of formation is defined as the change in enthalpy when 1 mole of a substance in the standard state is formed from its pure elements. The enthalpies of formation of different molecules can be found online or in the appendix of a chemistry textbook. Things to note are, the units for delta H are kilojoules per mole. The enthalpy of formation for an element is 0 kilojoules per mole, and an endothermic reaction will have a positive enthalpy of reaction, and an exothermic reaction will have a negative enthalpy of reaction. An example of method 1 is to find the delta H for 2NO plus O2 yields 2NO2, you have to find the enthalpy of formations for all of the 3 molecules. For O2, it's going to be 0 kilojoules per mole because it is an element. For NO, it's going to be 90.25 kilojoules per mole. And for NO2, it's going to be 33.18 kilojoules per mole. All you have to do is calculate it now. And in the end, the delta H is going to be negative 114.1 kilojoules, or kilojoules per mole, sorry. And since it's negative, that means that the reaction is exothermic. Method 2 is to find the energy of the bonds broken and the bonds formed. When a chemical reaction occurs, the atoms in the reactants rearrange their chemical bonds to make products. The new arrangement of bonds does not have the same total energy as the bonds in the reactants. Therefore, when chemical reactions occur, there will always be an accompanying energy change. In order to see what the energy of the bonds are, you need to know the arrangement of the bonds. The arrangement of the bonds of the reactants and products can be seen by drawing the Lewis dot diagram for each molecule. The arrangement of the molecules between N2 plus O2 yields 2NO can be seen below. The bonds of the reactants are the bonds that are broken, and the bonds of the products are the bonds formed. Energy is required to break bonds, but energy is released when a bond is formed. In reactions where the energy of the products is lower than the energy of the reactants, the reaction loses energy to the surrounding environment, therefore it is exothermic. In reactions where the energy of the products is higher than the energy of the reactants, the reaction absorbs energy from the surrounding environment, therefore it is endothermic. In order to find the delta H, you need to find the energy of the bonds broken minus the bonds formed. The energy of the bonds broken, you have to find the energy between N2 and O2, which is 941 and 495 kilojoules per mole. The bonds formed is the bonds between NO, which is 607 kilojoules per mole. So when you calculate it, the delta H of the reaction is going to be 222 kilojoules per mole. And since it is positive, that means that the reaction is endothermic. Method 3 of finding delta H can be found with Hess's law. Hess's law of constant heat summation, or just Hess's law, states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all the changes. With Hess's law, you are given the reaction for which you want to calculate the enthalpy change for, and however many other reactions that you will use and manipulate to find the delta H of the given reaction. For example, to find the delta H for 2S plus 3O2 yields 2SO3, you will use the reactions 2SO3 yields 2SO2 plus O2 and S plus O2 yields SO2 to find the delta H for the given reaction. When using Hess's law, there are 3 rules that you need to use / are allowed to use. Number 1, the reaction can be reversed. What this will do is it will reverse the reaction, but you will also change the sign of delta H. Number 2, the reaction can be multiplied by a constant. The value of delta H must also be multiplied by the same constant. 3, any combination of the first 2 rules may be used. In order to make the first 2 look like the last one, you have to reverse the first equation and multiply the second equation by 2. After you do that, the 2 equations will look like below. But remember, you also have to multiply and do whatever you did to the reactions to delta H. So for the first equation, you have to multiply by -1, and for the second equation, you have to multiply by 2. Once you do that, the things that will correspond will cancel out to form the given reaction, which will give you 2S plus 3O2 yields 2SO3. After that, all that's left to do is to calculate delta H. Once you do that, you get negative 792 kilojoules per mole. Since it's negative, that means that the reaction is exothermic. The sulfuric acid acts as a dehydrating agent, so a little water is needed to add to the sugar so that it's easier for the acid to strip the sugar of its water. Sulfuric acid is basically taking away the H2O from the sugar, and since the sugar is made up of carbon, oxygen, and hydrogen, pure carbon will be produced as the sugar will no longer have the oxygen and hydrogen. Water vapor and a mixture of water and acid are released, and pure carbon is left in the Dixie cup. That is why a fume hood is needed, because a mixture of water and acid are released, so we need to protect the students and our eyes from those gases, which is why we also wore goggles. As the sulfuric acid is added to the mixture of sugar and water, the sulfuric acid immediately starts to dehydrate the sugar, which is why you see the sugar turning black because the carbon is starting to be produced. The reaction in the Dixie cup gets hot and it releases a mixture of water vapor and sulfuric acid in water. The black stuff you see right there is pure carbon, and it is pretty hot to touch. Ay, muy caliente!
Can you call yourself a baker? Alright. We will now attack the beast. This is actually so cool. I don't know what this smells like, but...
Wow, that was pretty cool, wasn't it? Well, since the carbon was hot to touch, that means that the reaction was exothermic. But how do we find the delta H for the reaction? Well, you can find it by using Hess's law. This is the reaction equation. Sulfuric acid is not part of the reaction equation because it was just a dehydrating agent. Since we're using Hess's law, we need to have 2 or more equations to use and manipulate to find the delta H for the given equation. We will use C plus O2 yields CO2, which has a delta H of negative 393.5 kilojoules per mole. And we will also use C12H22O11 plus 12O2 yields 12CO2 plus 11H2O, which has a delta H of negative 5,640.9 kilojoules per mole. In order to manipulate and use the 2 equations to make it look like the given equation, all we need to do is reverse the first equation and multiply it by 12. once you switch around the equations, all you need to do is manipulate the delta H's of those equations so that what you did to the equations matches up to what you do to the delta H. Once you do that, all the corresponding things will cancel out and you will be left with the given equation, which is C12H22O11 yields 12C plus 11H2O, which, once you calculate it, the delta H is negative 918.9 kilojoules per mole, which means it's exothermic, but we already knew that.